Hello, and welcome to Lecture 20 on the topic of diffraction gratings. This is our fourth lecture in optics, and since we started optics with the discussion of wave optics, this is our fourth lecture on wave optics. Up to this point, we've talked about double slit interference, which is the simple case of two sources interfering, like two ripples in a pond. Then we talked about thin film interference driven by reflection and changes in wavelength. Then we talked about single slit interference, which was getting down to the details of Huygens principle and the fact that waves are composed of an infinite number of wave sources, thus they can diffract and make interference patterns even with a single opening. Well, we're going to go the other way in this lecture and talk about lots of openings. Now, it's also kind of similar to a single opening because after all, there were an infinite number of wave sources in that single opening. Well, here we have a finite number of many discrete wave sources. So kind of like double slits, these idealized sources, but we have a lot of them stacked on top of each other. It's a mini slit situation, okay? So let's take a look at our objectives. We want to learn how a diffraction grating is different from a single or double slit. What's the important differences? Okay. We want to understand how a diffraction grating allows for large, intense maxima that are very narrow, because that's really the defining characteristic of the interference pattern that is created by a diffraction grating. And we want to interpret how scientists use the diffraction grating to make precise measurements of light and wavelength, okay, or the wavelength of light. So here it is, G for grating, all right? And it's just called a grating, just like a cheese grater, because it's got lots of individual openings, okay? And a planar wave is coming in. We have a bunch of sources from all those gratings heading off to somewhere converge on a screen with the parallel ray approximation and a certain angle to that point where all those waves are going to superimpose on top of each other and create a pattern, okay? Now, what's that pattern going to look like? Well, we're going to see an example of it in the diagram down below, but first let's take a look at our key terms, which is just diffraction grating. What is it? Okay, it's multiple slits, just many of them, three or more, but in practicality, it's going to be hundreds or thousands, okay? Probably not hundreds of thousands. They're often called lines instead of slits. Now I'm going to use both terms, and it's just a term. It's just that lines, for some reason, has been associated more with diffraction gratings, whereas obviously it was always single slit and double slit. Okay. Now these mini side-by-side slits or gaps between painted lines on some transparent surface, and there's really kind of the reason, or definitely the reason, for the terminology lines. Okay. So that's it though. That's what a diffraction grating is. But what else can we say about it? All right. Well, one thing quantitatively is the diffraction grating has some length. That's how long the actual the actual thing that's manufactured is. How maybe it's like a microscope slide or something. And anyway, so that's its overall length. And of course, there's all these individual lines that are spaced a distance d apart, just like the variable d that we used for the double slit spacing. So we can define that, and often we do care about that number d, but just as often we care about the distribution of them. How many gaps are there in the overall length of the grating? And that would be lines per meter, okay? Common way to characterize the diffraction grating. And it just has units of inverse meters, okay? But what else can we say about the diffraction grating? Well, we can make this big statement here, and I'm just gonna read this out. Like double slit interference, the light from each slit in the grating has a path length difference, delta R, all right, with light from other slits, but, okay, this is what's different. The mini slits mean many combinations of path lengths. We're not just defining two paths like the double slit, we're defining lots of them. And we're not defining them in the same way like the single slit, where we can characterize them in the upper half and lower half, okay? So, turns out that the only specific value that set all the path lengths difference, I should say there are only specific values that set all the path length differences to some integer multiple of the wavelength. And what is it? What does a path length difference equal to an integer multiple of a wavelength mean? It means constructive interference, okay? So the point is that there's very selective, very specific combinations that lead to constructive interference, okay? All right, and that of course creates constructive maxima. All right, but here's the thing. Another way of saying that, i.e., the interference pattern has a lot of partial interference, but only narrow bands of constructive interference. think about it is that there's many, many ways to combine the different path lengths and have them not in phase, partially not in phase, but there's only very few combinations that lead to them being completely in phase, okay? And if they are completely in phase, then they're all going to be completely in phase of each other at that particular value, all right? Because once you have two of them in phase, two adjacent slits, well, now because of the equal spacing, that means that the next two are going to be in phase as well, okay? At least with the parallel ray approximation. And so what that creates then is that once they're in phase, they're all in phase. But as I said before, there are many possible ways to combine them to be out of phase, okay? So that's kind of the practical, the mathematical side, the leading up to the idea of the diffraction grating from starting at one slit, okay? But really the concepts here are more starting with two slits, double slit interference, and then kind of counting up from there, okay? All right, so I do want to say a word more about that in just a moment, but first I want to talk about their application because it just it strikes me when I lecture on this topic just how important diffraction gratings are, and also similar tools like prisms that split light up. But this ability to spread out light is so important to science because there's so much information embedded in light. Okay, and so I put it like this. So diffraction gratings are very important to science because the narrow bright bands that they create mean high selectivity for a particular wavelength. And that means all types of electromagnetic spectra can be investigated with a tool like a diffraction grating, whether that's a spectra from a particular emission, like an excited gas, or it's a spectra from a star, and we're looking for the gaps in that spectra to give us an idea about the molecules that are absorbing in the surface of that star. There's so much that spectra can tell us, and the diffraction grating allows that investigation to be carried out. Okay, so now onto the diagram I hinted at a moment ago. So this is the idea of going from two slits and kind of increasing the concept with more and more slits, approaching a diffraction grating that has hundreds or thousands of slits, okay? So let's think then. So if you just have two slits, you would have an interference pattern that looks like this, okay? Now again, we often see the peaks drawn lower as we move out. That has to do with the increasing distance and intensity falling off as a square of distance, okay? But here, instead, we're just kind of drawing them as equal intensities because we're assuming that that distance is marginal, okay? But the point is that there are still locations of maxima and minima due to the path length differences of integer multiples of the wavelength or integer multiples of the wavelength plus 1/2, which causes destruction. Okay, so there we go. There's our pattern for an n of 2. Okay, now what if we have 8 slits instead? Now we're not mathematically going to solve for the particular characteristics of 8 right now, but what would happen? Well, as I said before, now there are many ways to produce partial minima, right? Also some different ways to produce minima, okay? But there's only very selective ways where they're all in phase. And so that means that they're all in phase, but as soon as one of them starts coming out of phase, it falls off very quickly, okay? So you start to get to this point where before it was only 2 waves and they're out of phase. Well, it fell off gradually because they could gradually become out of phase, just those 2 waves. But as soon as they're not all lined up, well, then they start interfering with each other very, very quickly. So there's that precipitous fall off in intensity. Okay. It also turns out that because of the increased number of slits, that the actual peak, we won't solve this mathematically, but it's what you might expect. Now there's more sources, which means the intensity goes up. That means that there's just more energy here. It's before the energy was spread out. Okay. But now the energy is isolated in this peak. There's so little in between that energy has to go somewhere. Essentially, it's a proxy to the area under the curve here of an intensity versus angle. All right. After all, intensity is energy per time per area. All right. So, but the point being is, yeah. So now the peak must be much greater, right? And again, it goes up with the square of the number of slits. Okay. All right. And so then if you have 16 slits, then what you have is just more ways to get partial, mostly interfered waves, and then one particular way where they all are in phase. All right, so that's the concept behind having more and more slits and getting these very selective peaks that aren't just that. It's not even just that they're selective. It's also that they're very easy to see because they're very bright. All right, because they have most of the energy in them. All right, so diffraction grating. And one thing that I'd said before is that what comes up a lot is this idea of number of slits or slit spacing or line spacing. So N is the number of slits, and then L is the overall length of the grating. D is the spacing between individual gratings. So then that means that we just have number of lines is length of grating divided by space between the lines. All right. that's kind of a formula that comes up based on the ideas we mentioned. But our one big formula is this one right here. It should look familiar. This is the same as the formula for constructive interference for a two-slit, opening. Okay, so D here is just space between the lines. All right, in this case, there's not just two of them, so it's that constant space, and they're all evenly spaced, measured in meters. All right, theta is the angle between the midline of the grating and the nth max, because this is the formula for maxima for constructive interference. Okay, and I'm not going to give you one for minima because we don't care about all those mini minima, right? There's so many of them, right? And we only care about the maxima. Okay, M is just the order of the maximum. It does start with 0, just like with the double slit, because we have a central maximum. Okay, it's not like when we were counting minima on either side of the double width central maximum for single slit, because that's a different case. That's the one time where M doesn't start counting from 0. But in this case, it does start counting from 0. All right, and then lambda is the wavelength of the incident light, of course measured in meters, usually for visible light on the order of hundreds of nanometers. Okay, so one thing to note about this formula here is we can never use the small angle approximation. Okay, the small angle approximation is never used for diffraction gratings. That's something that really sets them apart from double slit interference. But there's a reason for it. It's not some arbitrary rule. It's because the distance between the slits is usually on the order, that's what I'm kind of representing here, so within a factor of 10 of the wavelength. So these are very closely spaced together. They're not maybe a half millimeter apart, which is often the case of double slit. These are just very, very tightly packed together. Now that's an assumption. Why is it? It doesn't have to be true, but that turns out that that's often the case. That's what people mean when they mean a diffraction grating, very closely packed together slits, okay? Not just many of them, but also closely packed. And because of that, that means Y, that's the actual distribution, the spatial distribution of the pattern on some screen, right, is large. And therefore, tangent inverse of Y over D is always going to be greater than 15 degrees. You can't use the small angle approximation. Tangent of theta does not almost equal sine of theta, right? They're going to be substantially different from each other. Our triangle is not some very long triangle where the hypotenuse is almost equal to the length of the longer side of the triangle. Instead, there's a hypotenuse that has two rather long lengths that are going to determine the length of the hypotenuse based on the Pythagorean theorem, right? So that's it. We have to actually use the trig. No big deal, but we can't use the small angle approximation. And this just shows the fact that, that here's the grating, right? This is the variables that I'm referring to. Here is theta, that's the angle to say the first maximum, all right? Other than the central maximum, y is the distance on the screen. And of course, the angle is determined by this sine inverse of the, well, at least for M1, just lambda, otherwise it'd be 2 or 3 or whatever times lambda, but just lambda over d, sine inverse of that ratio determines your angle. That's where where it's located. And depending how far away your screen is, that will determine your value of y. But the point being is that this is never a small angle. Theta is always going to be 30, 40, 60 degrees, right? They're at rather large angles. Okay, let's do our first example. So if a diffraction grating produces its third order bright band at an angle of 78.4 degrees from a light wavelength of 652 nanometers, find the number of slits per centimeter for the grating, all right, and then the angular location of the first order and second order, because after all, we're starting with the third order. Okay, all right, so here's our formula, right? Again, we're just interested in the constructive maxima, those narrow bright bands. Okay, and we were asked to solve for the slits per centimeter, so let's go ahead and find the spacing. So find D, all right? And so it turns out that the distance between any two adjacent slits is 2 microns, or 2 millionths of a meter. Okay, and notice the m equals 3, all right? And of course that I use the wavelength and the given angle and all that. All right, and so then I want to find out how many slits there are per centimeter, all right? Well, this is measured in meters, so if I take its reciprocal, that would give me how many there are per meter, and if I want them per centimeter, then I'm just going to divide by 100, because there's a lot more per meter than centimeter, okay? All right, so there it is, and these are just showing the conversions, so you can see then that I'm going to be left with something per centimeter. The meters cancel out, right, and I have centimeter, okay? So 5,000 per centimeter, all right? So there's going to be 5,000 slits per centimeter. Okay, hopefully that looks good. All right, I think, yeah, because I did take the reciprocal, that value there. I don't see my conversion here though, of dividing by 100. I don't know if I left that step out. It looks like I might have. I will double check this number, because it looks to me that although I wrote in here, I don't see that I divided by 100 to get this number. And so I think this actually might be per meter, because there should be, of course, less per centimeter. Yeah, So, okay, so that either check that or look back at my notes because that may be off. Okay, well in part B, I asked for the angular location of the first order and second order bright bands. So the good thing here is now that we have D, we're going to use that in the original equation, but just solve for some other angles. Because this angle, the 78.4, was theta 3. So I'm going to solve for theta 2, right? By just using D, plugging in, and I get, using sine inverse, 40.8 degrees. And if I do the exact same thing, I won't show the work, I get 19 degrees, all right? That makes sense, right? And again, not evenly distributed. We shouldn't expect them to be because, again, these are large angles. So it goes from 19 to 40.8, and then up to 78.4, right? And you might be like, well, they're kind of all multiples of 2. Well, yeah, sure, right? But they're not exactly, right? Okay. And then in C, will there be a fourth order bright band? That's an interesting question. What does that mean? Well, if you go ahead and solve for theta 4, plug in your calculator, right? You get undefined because you can't take sine inverse of something. Why is that? Because, well, there's not one. If it's undefined, that's a bad sign. There is no fourth maxima. And that just means that the angle where it would be is greater than 90 degrees. So it's not actually created. You can't create something on a screen if the angle is greater than 90 degrees. All right? Okay, let's do another example. So light of a wavelength of 500 nanometers is normally, so just, orthogonal, perpendicular to the surface. So normally incident on a diffraction grating G on the screen S. All right, the central line is at P, and the first order line is at Q. Right, just showing the locations, everything in the figure. All right, so the distance between adjacent slits in the grating is what? All right, so based on this information, what can we do? Well, since we know the length or the distance to the screen, and then we know for the distance from the midline, this basically is our y value to the first maxima, we can find theta. Right, so we'll go ahead and find theta with tangent inverse. Right, tangent inverse of 3/4, 36.9 degrees. Excellent. All right, we were told that that was the first order maxima, so that's an m of 1. So there's our formula. All right, m of 1. Go ahead and plug in. All right, so we got d is just going to be lambda over sine theta. All right, so we get 833 nanometers. That's the distance between adjacent slits. Didn't ask for the line spacing, it actually asked for d, so we're done. All right, next example. Now this one's a weird one, okay? It's very difficult to solve. You actually can't solve it algebraically. There's other versions of this problem that I could ask you, but I would never ask this way because you have to have the right software to be able to solve it. I just still wanted to bring it up because it is interesting that we can solve for it, either graphically or with what's called a computer algebra system, but let me get to it. A diffraction grating is built for astronomical measurements of the 21 centimeter line, a really cool idea in astronomy, which is a microwave indicative of atomic hydrogen and created by hyperfine splitting caused by electron spin states. There you go. All right. So how many slits per meter will this grating need if the goal is to distinguish between 21.000 centimeters and 21.001 centimeters, okay? Because you want to get that precise 21 centimeter line, okay? And you want to do that on the second order maxima, okay? Just for whatever reason, some engineering reason, and at an angular separation of 0.01 degrees, okay? All right, so then that you want to build this device. So the question was, then how far apart do the slits need to be? So how many slits per meter would you need? Okay, all right, so same formula. And we're going to have theta for 21 exactly, or at least to 3 significant figures centimeters, and then and theta prime for that other value, the value that's off, 21.001 centimeters. Okay, so we want the difference in theta, that's theta prime minus theta, okay, to be less than or equal to 0.01 degrees. Okay, well, we can use the formula for maxima to replace these two expressions, theta prime and theta. So just look like this, right? All I've done is just use that formula twice. So now I have an equation with a single unknown, okay? Because I know that m is 2. I was told we wanted on the second order maxima. We know what lambda is, and we know what lambda prime is, okay? In other words, lambda is 21 centimeters, right? I know it's a long wavelength, but these are microwaves after all. And then lambda prime is 21.001 centimeters, okay? So that means our only unknown is d. This is, again, a very difficult equation to solve, okay? So if you set it up like this, replace d of x, just show that this is how you enter in a calculator, and you solve for x like with a computer algebra system on the TI-89, very good device, right? Older now, but good. And then you find that x has to be 0.435 meters, or 43.5 centimeters, okay? Now, got to make sure that makes sense when you do something like that. So you check the solution, plug it back in, and we indeed get angles that are 1/100 of a degree apart. and they also make sense. It's a reasonable angle, based on the fact that this slit separation is about twice the wavelength, kind of right, typical grating to wavelength ratio. So we're good. Answer makes sense, checks out mathematically. So then we can go ahead and say, okay, well, if that's the case, then we're almost done because that x value is d, all right? So then we just take d inverse, right? So just literally just take the reciprocal, right? And 2.3 slits per meter, okay? Yeah, and that's a lot, right? That's like a huge, 2.3 slits per meter, what, they're 50 centimeters apart? Again, microwaves, okay? It's not for visible light. Our final example. If a diffraction grating has 610 slits per millimeter, then what is the maximum length wavelength that will show a visible third order maximum on a 4-meter wide screen that is located 1.2 meters from the grating? Okay, so this is being like, what's the highest maximum that fits? Okay, but instead of doing that question, instead you're solving for the wavelength that would have a particular maximum that fits on a screen. Okay, so here's the picture. There's the grating. All right. We want to have an M of 3 because we want the third order maximum. The overall screen has a length of L, curly L here, all right, and Y, the distance from the midline to the third order maximum, is just 1/2 L, okay? But we were given L, we're told it's 4 meters, and then D, the distance from the grating to the screen, is 1.2 meters, all right? And yeah, the screen is bigger than the distance because the idea is this is really spread out light, okay? So we see that tangent theta, just from the picture here, is 1/2 L over D, opposite over adjacent. So if we solve for theta, we get 59 degrees, big angle. All right. So then we're going to plug that into our formula for constructive maxima, okay, and then solve for lambda. All right. But we don't have D yet because we were told that there are 610 slits per millimeter. So if we solve for D, and we have here, and this is unlike the previous one. I didn't goof and leave off a number. So we have 610 slits per millimeter to the -1 power, and then multiply that by how many meters there are per millimeter, and we end up with, because of course there's a 1,000th of a meter per millimeter, and that will cancel everything out except meters. So we're left with meters and a spacing of 1.64 microns. Okay, excellent. So that means that lambda must be the spacing times sine of the angle given divided by the order, m equals 3. And there we go. We find out that the visible light that would work, the longest visible light that would actually fit on the screen out of third order maxima, is 469 millimeters. All right. So there is our final answer. Put a box around it. We're done. All right. And I did forget to put a box around it, but I did it now. Okay. So those are just kind of variations on the types of problems that you would do with a diffraction grating. Hopefully this seems like a straightforward continuation of the ideas that we've presented within this chapter, all about light interference and light behaving as a wave. This concludes our lectures of talking about light behaving as a wave, and we're going to start talking about light behaving as a ray, which really is just a helpful tool for dealing with optics like mirrors and lenses. So that will be the next lecture. I hope it is something to look forward to, and thank you so much for watching this lecture.